My name is Dr. Shobhana. I am from IIT Jodhpur. I'm Associate Professor in the Department of Mechanical Engineering and also currently serving as Associate Dean R&D in our institute. I first like to thank the organizers for organizing such a wonderful conference. I had a really great time, especially in the gala dinner yesterday. I hope all of you also enjoyed equally. Today I will be talking on the development of phase change material-based thermal control systems for space applications. Probably many of you have been hearing about plasma simulations from past 3 days. Now this is a different taste which I'm going to give you today. I hopefully expect also that you will have some insights from this study. So definitely it's not any magnetized fluid, but unmagnetized fluid that I will be talking today. So moving forward with this talk, let me quickly show you the table of content which I will be covering today. I'll talk about phase change materials, as many of you might not know what these materials are and how they can contribute in controlling the temperature in space systems. I'll also talk about what makes these devices important and what are the challenges that space thermal environment poses in order to design them. And then I'll take an example of a case study that we are looking at and give you some insights which actually enable any engineer or a scientist or researcher to look into the behavior of these phase change material designs and devices. Moving forward, phase change materials. So what these materials are. So in layman terms, I shall explain it to you that these are the substances that absorbs a large amount of heat or release a large amount of heat when they change their phase, especially during melting and solidification. So for example, during melting, what happens when a phase change material actually transitions from solid to liquid? What usually happens? They absorbs a large amount of heat from its environment, equivalent to the amount of latent heat of fusion. And what they do, they actually store this heat into their internal structures. And what happens next when they change their phase? During solidification, for example, they basically releases this heat which they stored previously during melting cycle to the environment. And all this process of phase transition happens at a constant temperature. So basically, this potential that these phase change materials have, that they transition from one state or one phase to another phase at a constant temperature, particularly so-called melting temperature or phase change temperature, makes them a potential candidate to basically act as a buffer whenever we want to control the temperature fluctuations into a desired range. So that makes it a very appropriate candidate whenever we talk about temperature control on terrestrial environment as well as in space environments. How do they work, which I already explained to you briefly. Another advantage is what these materials actually encompass is that they act at nearly isothermal temperatures, which makes them a very best candidate for storing energy or to buffer temperature fluctuations in a desired range. As I mentioned, because they transition their phase at constant temperatures. They also inherit high energy storage capacity due to high latent heat of fusion, which is usually 1 to 2 order of magnitude higher than any sensible energy material, which usually stores energy in the form of specific heat, for example. They are better potential and making a candidate with a higher energy storage capacity. So they are not only able to control the temperature, but they can also store it with a better capacity than any other sensible material out there. They also work passively. You do not need any active device or any mechanical means in order to operate phase change material devices anywhere. They are also suitable for repetitive transient on and off cycles, especially where the temperature fluctuations exist. Especially the heat loads, whenever they are transient in nature, you can go ahead and utilize phase change materials to buffer those fluctuations. So all these properties combined and advantages combined, PCMs can be used for temperature control and energy storage material very widely across applications. So having this known to us, let's move about what different type of materials are available. So as an engineer or a researcher, you would like to know that what material I shall work with. So there are numerous classifications out there which will enable you to select an appropriate phase change material for your applications. Based on material type, for example, if you look at the first one, I hope my laser pointer is working properly. Yeah. Based on the material type, based on phase transition, based on melting point. And let me say, especially a good guidance comes from melting temperature. So depending on what temperature range you want to operate your device at and you want to control the temperatures within the range, that will guide you to make a selection of your phase change material. The primary important ones are often organic phase change materials, which you see on the left-hand side on the screen. Paraffins are the commonly used phase change materials in space applications, particularly because of their neutral nature. They do not react with the container materials that fast, and they're also cheap. And their temperature aligns very well with the instruments where we want to control the temperature. Salt hydrates, inorganic PCMs are also commonly utilized for high temperature energy storage devices on terrestrial applications, especially solar thermal ones. Eutectic phase change materials, especially inorganic kinds, are also being used for storing or buffering the temperature changes at very, very high temperature ranges beyond 600 degrees Celsius, for example. These are available in the market at a wide range, from the very pure form, granule form, to the encapsulated composite forms, and also sometimes they are being available in the form of metallic sheets. So you can utilize as per your requirement to design a system which is used for temperature control purposes. So moving further from here, what is their role in space systems? This is not new that people are in space applications have been using phase change materials. They are being in use from last over 50 years, in fact. However, designing them has been a challenge because of the challenges associated with the space environments. But before I move to that slide, I would like to just show you where are they commonly used. They are being used especially for instrumentation cooling. As you know, in the space systems, in addition to payloads, we also have very sensitive instruments which have to operate precisely within a desired temperature range. Otherwise, they may not be giving you appropriate or accurate measurements, or maybe will not be functioning properly. So in order to function or make these devices operate in these environments and temperature ranges, phase change materials are commonly used. So what they do, they basically ensure that there is a precise temperature control, and these devices shall give you the measurement or the reading as per the accuracy of their design system. They're also commonly used in satellite thermal control. As you all probably know, that satellites basically orbit around the Earth or any other planetary body. When they do so, they experience highly temperature fluctuations. Especially when they are in direct sunlight, they are experiencing extremely high temperature. And when they are in shadow phase, they are experiencing extremely low temperatures. And during this orbiting period, they are experiencing fluctuating and on and off type of heat load cycles. And in order for an instrument to function appropriately within these dynamic cycles or heat load cycles, you need to ensure the temperature remains in a desired range so that these devices shall perform appropriately. So what happens, PCM basically are integrated with these devices in order to absorb the excess heat in the direct sunlight phase and actually release it and come back to the optimal temperature range during the shadow phase. So PCM stabilizes temperature in these satellites by doing that mechanism. Spacecraft thermal protection. Often what happens when these satellites or any space, infrastructure, when it comes back to Earth environment during re-entry periods, they are experiencing high temperature loads during that period. And during that re-entry, if you will have a multi-layer phase change material thermal insulation around those, you can prevent the excessive heating, and so you can actually avoid the structural damage that satellite may have or could have during those re-entry periods. So there, yeah, they are commonly used. Another is space habitats. These are only some of the applications. There are numerous ones, but I'm only projecting the major ones where these PCM devices are very, very commonly used. Space habitats, especially for long-term missions on other planetary bodies, you see that we have to ensure that the temperatures are comfortable for the crew which has been gone there, and also for the equipments to operate for a longer term in a desired temperature range and give you precise measurements. Then again, PCM devices have been integrated strategically into these habitat designs so that these missions could be successfully completed. I'm also giving the students for their good view. These are some examples of these PCM capacitors. These are very small boxes of variable size, they are being designed for different heat loads. And they're very simple containers of metals which are compatible with the PCM materials filled inside them. And you simply place them on any power electronics, for example, which is dissipating heat. And what you are doing is you are actually absorbing that heat from those devices, keeping them or storing them into phase change material for the heating or melting period, and then release it or radiate it out into the ambient, which is your space probably, just to get rid of that excessive heat which has been generated. So you can store it, probably convert it for any other supplementary power device, or you can even dump it out into the space. So these are some capacitor designs, very simple designs commonly used, and are being very commonly in applications by ISRO, ESA, and even NASA. You can find very detailed documentations about them. So moving further from there, what makes the design of these devices complicated and important, and what actually makes us interested in these devices? Space environment poses extreme challenges to the development of such PCM devices. What happens? Because in space, we experience extreme temperature fluctuations, which I already explained earlier. What happens that these devices are exposed to extremely high temperature during the direct sunlight and experiences very low temperatures during the cold vacuum periods. And you can see on the left-hand side of this screen that there are some transient heat loads. So they are not continuous. They are abrupt or they are intermittent. So whenever there are heat loads, temperature fluctuates pretty high. And if you integrate it with PCMs, you can actually get rid of this high temperature peak. So you are actually buffering this away so that there is no harm to the device or equipment which is actually generating this heat. So basically, these sort of working functions can be dealt with these sort of phase change material devices in space. In space, we also commonly experience low and microgravity environments, especially the satellites that are orbiting around low orbit satellites probably. They are experiencing low gravity or microgravity conditions. Landers, rovers, other space infrastructure on other planetary bodies, they're experiencing different ranges of gravitational forces over there. So basically in space, you know that there is a range of variable gravity forces that actually, again, makes the functioning of these devices complicated because it's not going to remain same. It does change during maneuvering, re-entry, launch period, and so on and so forth. So one has to take all these changes into account when they are developing these temperature-controlled devices based on phase change materials. Another thing in space, you know that in different stages, we get rid of the hardwares, right? What happens? Because we want to have a maximum payload weight over there. So we have very, very limited resources that can actually control the temperatures in space. So then it becomes really, really critical for anybody to keep in mind that whatever design or temperature control system we are sending in space has to operate under these variable conditions of temperature and gravity so that one system can function all during the period you are sending it off. Another is, whatever we send in space, it's quite expensive and very, very sensitive to temperature changes, and they also have to be very precise. So what happens, in order to secure their safer operation, you have to ensure that they are being temperature controlled for their better performance. So they require precise temperature control to maintain their best performance or optimal performance, so to say. For example, for students, just to understand that a mission could even fail if your battery is not charging and discharging in a desired temperature range, or if your computer or the sensors that you have on board in space, if they are not operating in a desired temperature range, then what could also happen, or any other mechanical part, for example, so to say. It could all lead to, even a minor deviation could lead to the mission failure entirely. And no one wants it because they are quite expensive. So again, these are, again, a stress on any engineer or researcher to develop a design that should be robust enough in order to keep in mind all these combined effect of this space thermal environment in mind. Moving further from here, what we did is we actually started looking into these challenges that this environment poses and did some case studies. I'm not presenting today all the case studies, but one where we looked into the combined effects of variable gravity in addition to orientation. Because that system which we were developing is actually meant for spacecraft, and what happens when you launch it in a lower orbit of Earth or even a higher orbit, they actually tends to orient when they are in the orbit. I will be able to explain it in the next slide. So keeping in mind that gravity is a very critical parameter because it is also one of the basic forces in nature, any material of a finite mass can pull any other material around it due to this, basically due to this force. So basically in space, you are experiencing variable gravity during the launching period. You can see here during the launching period, re-entry period, maneuvering period, so on and so forth. And thus, we have to keep in mind that the variable gravity shall impact the performance of phase change material devices. But how? That should be a question, and we addressed it in our case study. Another thing is these transient conditions actually disrupt the phase transition process a lot. So far you have been looking into the plasma simulations and how the plasma might behave in different scenarios and situations. Here we are going to look at how the phase change phenomena of a phase change material will behave under these varying conditions in space. So we shall see it in the next couple of slides. Another important parameter that we considered in our case study is orientation of these devices, because once you have these devices on board, meaning on spacecraft, they tend to orient with respect to the heat flow direction. Because once it is mounted in your system, once it is integrated, you will have a heat source on one side and the sink on the other side. And if the orientation of this heat flow is not aligned well enough with the gravity direction or gravitational pull, what could actually happen? We will have local heat transfer areas or solidification areas, melting areas, which could lead to inefficiencies into this system. It may not be able to operate to its best possible efficiency. So you have to find out those lackings by studying their behavior in varying combined effects so that you shall determine what will be the optimal operating conditions for these devices to perform so that you can control them as well. So you can see, especially students from the slides, that once the satellite has been launched in an orbit, so here you can see the orientation of the satellites, different orientations, in fact, when they orbit the Earth. So with respect to the gravity, because the gravity here is going to actually influence the heat flux direction inside these devices, and so does the buoyancy forces sometimes. So that is something very important we have evaluated in our studies. So I'm going to come back quickly to the problem definition over here. This is a very simple device, which I also showed you previously. It is very small PCM capacitor. It is 20 by 20 mm dimension over here, which we are developing in our lab also. It has been filled currently with an organic PCM paraffin, having a Prandtl number of 71 and a melting temperature of around 29 degrees. So you can see that what you can actually develop, you can simplify this model and develop a three-dimension thermofluid model. We worked with two-dimensional because of the higher complexities in the fluid nature, which I will explain in the later slides. But this is the two-dimensional container we sort of designed as a domain in order to investigate the combined effect of variable gravity in the phase change Rayleigh-Bénard system. Rayleigh-Bénard system, I hope many of you might have studied previously. It's a classical system where the fluid has been heated from the bottom side, right? And then you get to see the changes in different flow regimes. So here what we are doing, but here we are not dealing with the classical single-phase Rayleigh-Bénard system, but phase-change Rayleigh-Bénard system. So here in our two-dimensional container, we are heating the bottom surface so that the phase-change material that has been filled initially starts to absorb that heat and melts as it absorbs the heat equal to the latent heat of fusion. And what happens? This PCM again progresses. It keeps on melting, and what happens? Then the entire domain becomes liquefied, right? The PCM melts completely and stores the amount of heat which is the equivalent or proportional to the volume of this entire domain as well. And often that is a design parameter coming from the heat load. So you get to see this domain, which is very simple. So bottom surface has been kept hot. Top side has been kept as a sink, which could be a radiating surface. So here you can see on the extreme right-hand side of the screen that this is an instantaneous illustration of a phase where the PCM has been melted and reaches approximately half of the domain. So what happens when the PCM melts? It liquefies. And when it liquefies, you get to have these convective currents moving upwards and downwards into the domain, and the half of the domain remains solid. I hope you are able to see the blue part on the top. That is the solid PCM, which has yet to melt, and this is the bottom part, which has been melted because of this constant heat source. Right now, what you are observing is an actual scenario that this interface between these two phases is not uniform. It's basically curvaceous. And what happens, we are actually simplifying this curvature by making an average height of this interface from the bottom surface, because we definitely have to evaluate the efficiency of the system. That is just for the evaluation purposes has been done. This interface, I hope you are able to see, if I'm able to track the pointer over here, yes. This is the diffuse interface. I hope you're able to see. It's a bit thick of a line, not very, specific line, because it is representing the blend of solid and liquid phase change material available at the interface. Now, you can see all the boundary conditions that the sides have been kept insulated. Only top and bottom are the heat source and sinks. And these are the conditions that our model has been provided with in order to simulate this melting behavior or phase change behavior. Now, not showing you the mathematics of it, you can definitely refer to these papers which are quoted at the down, or you can just contact me. I shall be giving you more details. Here, what I'm going to present to you is the temperature field in this domain when the melting occurs. Right? And you get to see different phases of flow behavior also. This is a point location I hope you are able to see from a dark black dot. It's just an arbitrary location where I want to show you this instantaneous temperature profile, because this instantaneous temperature profile will tell you the instabilities which will occur when the melting progresses. So just like in the classical Rayleigh-Bénard case, you have linear instability, the first instability, where the buoyancy forces actually overcomes the viscous diffusive forces. And then the second stability, which is actually as a result of, destabilization of the density at some point in the domain. So you get to see both in here parallelly or simultaneously as you get to see this qualitative illustration. So I hope you are able to see that initially the fluids actually melt diffusively. There was a planar interface, then it converts into plumes, which again merges together to form a larger plume. So here you are seeing the temperature field overlapped with the velocity vectors, so that you also get to see how the flow direction actually changes as the PCM melts with the time, or melting progresses with the time. I can again play it for you just to show you that what happens here, that with time, diffusive period starts, and then the plume formation. So basically, at that particular point, convection onset happens. Initially, the heat was being transferred by conduction process, and then as the buoyancy forces overcomes the viscous forces, convection starts. And this convection definitely is weaker in the low gravity situation, because I'm only presenting for the standard gravity case as a benchmark, so that you will be able to compare the future cases, which I will be showing you next. But the important thing is we were able to identify the points, instantaneous time periods, where the instabilities also occurs, because you get to realize when the heat transfer expedites, when the melting will expedite, so that you shall operate your devices into those zones or instantaneous times and improve the efficiency afterwards. So this is just for the students to see that how the melting behaves in a standard gravity situation. We thoroughly investigated for a very, very wide range of low gravity cases, not showing you all the cases, but a very good summary of it. So here what we did, we are actually just analyzing different flow regimes. What you get to see here is the first phase regime, which is the diffusive regime, where the heat transfer occurs by a diffusion process. And that is something is represented in terms of dimensionless Nusselt number. You can see that it is actually approximately 0 up to the Rayleigh number equals to 10 to the power 3. This represents the regime where the melting happens pretty slowly. It is characterized by a planar interface of the phase change material, and one gets to see this is something to get avoided, of course, or at least it's a starting phase for us. Moving forward, soon after this period, we get to see the onset of convection. So at this point in the standard gravity, you get to see the convection begins, and which is reflected by the Nusselt number, that it suddenly rises with a very steeper slope. And this corresponds to the earlier diagram where the plumes will form and they start to stretch vertically. So that persists. This regime persists up till certain time, of course, to an effective Rayleigh number 10 to the power 5, where the plume evolution is happening. Here in this diagram, this black solid line is basically our simulation results, and we compared it also with the classical Rayleigh-Bénard data, which has been shown by the solid red lines over here. The data was not available for these first two regimes, but you can see the later, at a higher Rayleigh number, the data was available, and we best fit it also. What happens when the second instability hits? After that, what you get to see, fluctuation starts to emerge. And with the increase in the Rayleigh number and time, the amplitude of these fluctuations are also going to increase. Basically, what is happening here in this plume evolution phase, where the fluid flow is pretty periodic and structured, it gets too chaotic. It actually becomes oscillatory, and then with the progression of melting, it becomes totally chaotic at some point. However, we haven't observed the fully turbulent regime, which definitely shall arise if we would have gone a bit higher in the Rayleigh number range, which we are trying to observe now in the future studies as well. But this is something we actually observe, which has also been observed previously by many researchers in single-phase Rayleigh-Bénard systems. In two-phase Rayleigh-Bénard systems, very, very few or handful of studies have been there which are quoting this. So this is one of the few studies that we have actually published also, has been recognized that how these regimes are evolving in a phase-change Rayleigh-Bénard system, and also their sequential evolution with time in different gravity conditions. So I'm not going to show all results again, but to show you that we mapped all these regimes in a single curve. So if one would like to see that what would happen when the gravity actually reduces from standard case to low case, you can clearly see what happens, that the time taken by the phase change system in a low gravity case is longer in melting, because of the weaker buoyancy forces compared to the standard gravity cases. So basically what you get to see over here is that as the gravity reduces, the diffusion time taken by the system increases. And it continues to be seen at early onset, second instability, as well as the oscillatory flow regime, even the chaotic one. What it tells us that in the low gravity environment, basically melting of the PCM reduces. The time taken by the PCM to fully melt reduces significantly, but by what rate, that is what we are able to quantify from these plots over here. So what we also did, we used this information and we best fit it in order to know that if there is any correlation available between these heat transfer numbers and the Rayleigh numbers as well as the Reynolds number, so that one does not have to go through these extensive CFD or iterative simulations. They shall be able to scale or design a system of any size with this information. So we did that in future. But before that, a lot of people were also curious in knowing what is the critical Rayleigh number where these instabilities will occur in the low gravity situations. So for those, there is some relationship we have established. So here you can again see that the onset basically has been delayed quite a bit for a low gravity cases over here. So this critical Rayleigh number will enable you basically to tell that when these instabilities will hit, when the heat transfer will be dominated by convection mode, so does the heat transfer efficiency shall be increased. And it will tell you how to control your devices in such a manner, in what regime you should operate your PCM devices, so that you will be able to absorb heat faster, rapidly from any system. So this is something we established a relationship with the Rayleigh number also, which is again you see is a decreasing function. You can see not too much because slope is small, but it is a decreasing function. So one shall actually able to determine what will be the critical Rayleigh number for with relation with the gravity basically, because gravity has been an inherent part of this Rayleigh number over here. So whatever gravity you have in mind, you will be able to know what shall be the critical Rayleigh number, meaning what shall be the onset of convection in that case for myself. So these relationships has been established. Next is, this is again for the students just to have a glimpse that how the PCM melting rate reduces when we move from standard to low gravity situations. So you shall be able to see this is just a comparison between 0.6, 0.4 and 0.2 gravity conditions, that how fast it is at a higher gravity situations and how slower it is in the low gravity situations. There is another peculiar phenomena which may be not able to see until you see these videos again and again, that the sizes and the number of plumes that arises under these different gravity conditions are of interest again. They are also different, which actually tells you a lot about the forces and their dominance. We also did a separate study on them, not showing it here, but just in case if anyone would be interested, they can again refer to the published articles. Again, as I said, that we did look into the orientation also. So we did look into different orientations spanning across 360
Shobhana,
degrees.
you've done your 30 minutes, so you can
Okay, I'll be now wrapping up. Different gravity orientation. So we actually looked at the combined effects also, and we did also do a statistical analysis on these, which has been recently published in 25 in the Physics of Fluids. One who might be interested can go and check those results out. As an engineer who was interested in looking into the flow behavior and different evolution of these regimes, we were also willing to cater to any engineer or researcher in order to get the information out of these extensive analysis so that they can scale their system for experimentation or even to predict the behavior of a system if they are willing to develop any. So we did use the data in order to create or establish the functional relationships between the dimensionless parameters, which will tell you not only the performance, but the design aspects of these systems. So we did develop scaling relationships between Nusselt number with the effective Rayleigh number and Reynolds number with the effective Rayleigh numbers in the low gravity environments, and in addition to orientation also. So again, I'm not able to give you explanation because of the lack of time, but this is available. Another thing which I'm going to end this presentation with is, while we were studying all this, we also realized that in the microgravity scenarios, there is another phenomena that could contribute to the faster melting of phase change materials that is called thermocapillary. So because sometimes these are the interfacial forces which can positively contribute to the melting, we did also look into that, again numerically via simulation, which enabled us to utilize this bottom part, which always remain unutilized. So with the help of thermocapillary effect and a dual PCM approach, we are able to even melt this 10% remaining PCM, which was earlier remaining unmelted in the conventional designs. So that is another contribution which we made, and this study has also been published successfully and appreciated. So you shall also take a look of it and try to see that how the limitations can be converted into opportunities and improve the efficiency of your existing systems. So I'm going to move forward, just quickly ending this. This is just a strategy to select an appropriate material in your device. And these are the comparative results which actually proves that with the help of dual approach, you are able to actually achieve higher efficiency, storage efficiencies, and also the storage enhancement factors. So this is just for the students to come up with some numbers in order to quantify and prove that your devices are actively behaving better. Here are some conclusions, or I shall say summary of the things or the case study that I today presented, that we see that how the gravity basically decreases or weakens the buoyancy forces, which actually slows the PCM melting rate, and the number I'm quoting here is 80%. So if you're going from standard gravity to microgravity situation, your melting rate reduces by 80%, which is quite a bit. So you have to keep in mind in which gravity ranges I'm going to function in, and accordingly you can optimize your system design and operating conditions. Criteria we developed, so we established criteria for onset of convection, which again, not only for gravity cases, we also established it for different orientation conditions. We also established functional relationships, scaling relationships, as I said, again in a power law behavior form. By the way, these scaling laws have been verified with the established data sets also, so just in case anyone is curious. However, they are limited. So you can understand the validity range for these scaling relationship remains a moderate Rayleigh number range. So we are not able to get the higher Rayleigh number, which is the scope for our future studies, because there you get to see fully turbulent regime as well. Moving further, we also demonstrated successfully the dual thermocapillary enhanced PCM approach, which is able to enhance the total storage capacity up to 44% and reduce the melting time by 88%, you can see that. So future work is actually carrying on in our lab where we are actually looking into different Prandtl numbers. Prandtl numbers meaning you are spanning across different sort of materials and their thermal behavior in these temperature conditions. So how will that behave? That is what something our next focus on. And we are looking into different aspect ratio in order to understand the boundary behavior also. So that is something I'm stopping with now. If anyone has any question, feel free to ask. Otherwise, they can contact me separately also for much more details. Thank you.
Thank you, Shobhana. So we'll take one single question because we've sort of exceeded the, yeah.
Thank you for your well-organized and interesting talk. So I have a basic question, in fact. So how do you critically quantify low gravity and microgravity?
Can you repeat it for me, please?
How do you critically quantify low gravity and microgravity?
Okay, so low gravity is something we took an motivation from these values, if you notice, that how in different planetary bodies the gravity changes. So you see, we were just going selectively just so that the gravity doesn't go zero. In microgravity, basically, the magnitude goes so small up to the order of 10 to the power minus 6. So negligibly zero, virtually zero, you can say. In those situations, there is no role of convection. So in our study, we kept a range selectively up to 2.2 G so that the meager convection currents do still exist. So that there you get to see a bit of buoyancy forces over there. But when you talk about microgravity, convection at all is absent. That is why there we had to function with thermocapillary effects in order to enhance the melting process. So that is how they are different in terms of their magnitude, and because of their magnitude, the forces are different which are acting.
Okay, in continuation, I have another question. So out of the orbital zones, Leo zone, then Meo and Geo, which one best fits to microgravity? Geo?
Sir,
Leo.
Please repeat it
No,
again
orbital.
for me.
Leo zone, Meo zone and Geo zone. Orbital zones, lower orbital, lower Earth orbit, then middle Earth orbit, geostationary orbit.
I think we'll take
You
this
have
discussion later because
Yes,
we are-
I'm
Okay,
sorry,
thank you,
I'm not
thank you.
able to make
Thank
sense of
you.
this. Mic is pretty loud, that's
Okay.
why. Otherwise,
Okay,
it's
okay,
fine.
okay, thank you. We may discuss later.
Yes, thank you.
Thank you, Shobhana, for an interesting talk.
Yes.
So